Multi-million-dollar corporate acquisitions and enterprise vendor selections frequently end in failure. These high-stakes decisions often collapse not from a lack of data, but from the overwhelming pressure of processing it. In 1956, cognitive psychologist George A. Miller proved that human working memory has a strict bandwidth limit. A person can effectively hold and process only about 7 items at any given time. This illustrates what happens when a strategic choice demands more than the brain can handle. A decision with 7 criteria is manageable, but introduce 15 or 20 competing variables and the mental connections break down. This is cognitive overload. The human brain cannot juggle 20 variables simultaneously. Instead of gracefully processing the information, the mental workspace effectively crashes, shedding crucial data points. To cope, executives often perform a heuristic retreat. They abandon complex variables like long-term risk or cultural fit and collapse the entire decision into a single, easily digestible metric, usually immediate cost. Significant strategic failures rarely stem from a lack of intelligence in the boardroom. They are the direct result of ignoring this strict biological limit on human processing. When cognitive bandwidth is exhausted, a vacuum opens up. Unexamined biases and hidden preferences rush in to make the decision instead of objective data. This environment breeds the hippo effect, the highest paid person's opinion. In a room without a structured framework, consensus artificially and inevitably gravitates toward the leader's preference. Relying on executive intuition under these conditions creates a deceptive sense of alignment. It produces a consensus that rapidly falls apart when subjected to rigorous scrutiny. The structural solution to this biological bottleneck is the analytic hierarchy process, or AHP. Developed in the 1970s by Dr. Thomas Sadie, it provides a mathematical framework that organizes complex variables into a manageable hierarchy. Without this process, executive intuition often masks unexamined bias. AHP replaces that ambiguity with a system that maps individual priorities into a consistent, measurable model. The framework begins by decomposing the complexity. It breaks a massive strategic problem into a structured hierarchy, ensuring the brain never attempts to process the entire problem at once. Stakeholders then execute pairwise comparisons. By evaluating exactly 2 criteria against each other in isolation, the framework eliminates multivariable overload. Within this matrix, human judgment is quantified using the Sadie scale. By assigning a value of 3, the stakeholder mathematically declares cost is moderately more important than quality. This process repeats. The matrix populates as participants log isolated judgments, building a robust dataset one comparison at a time. Standard 1 to 10 rating scales allow executives to mark every factor as highly important. Pairwise comparisons force explicit relative trade-offs, preventing participants from avoiding difficult choices. Because this data is entered individually and anonymously, the hippo effect is neutralized. The highest paid person has exactly the same mathematical weight as the subject matter expert. By strictly isolating each decision and controlling the cognitive load, the pairwise method bypasses Miller's law. It translates subjective human intent into a structured, usable dataset. However, human logic is rarely perfect. Over the course of a long meeting, executives will frequently and unknowingly contradict their own stated priorities. In decision science, this is known as an intransitive relationship, a circular loop of preference that defies logic. We can see this flaw appear in the matrix data. A stakeholder might state that cost beats quality and quality beats speed, but then claim that speed beats cost. This creates a literal rock-paper-scissors scenario inside the data, where every priority defeats another in an endless loop. While intransitive logic is functional in a game, it disrupts the logical foundation of corporate strategy. It means the decision-maker is effectively guessing. Left unaided, executive intuition is riddled with these invisible contradictions. Decisions built on this flawed logic are fragile and prone to failure. To ensure the data remains valid, the framework employs the consistency ratio, a metric used to identify and flag logical contradictions within the matrix. This formula calculates how far a set of judgments deviates from perfect logic, compared against a baseline of pure random noise. The acceptable threshold is a ratio under 0.10. A flagged score of 0.25 indicates the boardroom's logic contains significant contradictions. In the field, a high consistency ratio forces the room to pause. Consultants can locate the exact point of contradiction in the matrix and require executives to explicitly justify the discrepancy. This metric depersonalizes corporate conflict. It shifts the debate away from clashing personalities and focuses the room entirely on correcting flawed data. The consistency ratio provides an objective audit of strategic logic. It exposes the exact moments when supposed leadership alignment is actually indistinguishable from random noise. Once the group's logic clears the consistency threshold, a final mechanical question remains. How do we extract one definitive strategic decision from a room full of competing variables? The answer relies on linear algebra, specifically the calculation of the principal eigenvector. Think of the comparison data as a geometric block filled with vectors. When a matrix transformation is applied, most of those arrows twist and change direction. But there is one specific arrow that stays pointing in its exact original direction, unaffected by the distortion. That is the principal eigenvector. In the boardroom, the minor inconsistencies of human judgment act as distortion. The eigenvector isolates the invariant, mathematically consistent preference of the group, ignoring the noise. By calculating the eigenvector, the framework delivers a weighted ranking of priorities that is rooted in the mathematical relationships between judgments, making the final result transparent and significantly more difficult to bias. This methodology offers a dual guarantee. The eigenvector extracts the priorities of the organization, and the consistency ratio proves those priorities are logically sound. Today, modern AI enhancements build directly on this math. Intelligent systems can automatically scan the context for strategic blind spots before comparisons even begin, and generate narrative justifications based entirely on the eigenvector data. When millions of dollars are on the line, organizations do not need louder voices or unexamined gut feelings. Boards and shareholders require explainable audit trails detailing exactly why a strategic choice was made. Replacing chaotic boardroom intuition with the rigor of linear algebra secures that audit trail, transforming strategic uncertainty into a confident, data-driven reality.